Hello, Calculus 6.9 Part 2, trying to do integrals with inverse trig, the opposite of what we did yesterday with derivatives. So today there's three main formulas that you want on your card, which are on the notes paper that I made you, which is if you have a derivative of a u on top, and on the bottom you have an integral with an a squared minus a u squared. That's always going to make inverse sign by putting u over a. The u always has to be a thing with a variable in it. The a can only be a thing with numbers in it, no variables. And since the problems are going to have squares and the answers are not, we're going to do a lot of roots today in doing these problems. So if this is like a 9, 9 is caused by 3 squared. So a 9 in a problem is going to make a 3 in an answer, that kind of thing. If you don't see a root, you probably have an inverse tan problem. The inverse tan problems have numbers adding variables on the bottom. And if the order is out of order, no harm there. Adding in any order, not a problem. The tan has an additional feature of 1 on top of the a before you do the tan code. If you see the root has another thing in front of it and has variables minus numbers, instead of this had numbers minus variables, numbers minus variables is sign. Variables minus numbers is secant, only if it has this extra thing also in front. That has like tan, the 1 over a item in front, and it also has bars around it. All of these fractions are always u over a. Those three things want to be on your card. We're going to use those constantly when we step to the right. Before I do that, I'm going to get out of the way one misfit problem, because this does not fit any of these patterns. This looks most like this, because there's no roots in these on the bottom. But this would tell me that my a is a 1, and my u should be an x. And the derivative of x would only be a 1, and there's all this crazy stuff going on up top. Like, this is way meaner looking than anything else here, or I don't know how far right you can see on the board right now on the camera, but this is ridiculous looking right now compared to everything. So there are some problems in the homework that won't fit a format, and we have to go with an old skill called integration by substitution, where you pick a u. You pick a u to be a bite-sized, ugly piece of this. But don't get too greedy and take too much. So this is just the right size. Inverse tan of x is pretty ugly, but not impossible. So if you get problems that don't fit a format, pick a u to be something kind of ugly. Figure out the derivative of that. That's a problem from yesterday. Tan's derivatives yesterday, we did 1 plus stuff squared on the bottom, the derivative of the stuff on the top. That's what we were doing on the 1 to 22. And if we now look at this problem, there's an e that we didn't account for, but the power we renamed u. And all of the rest of this fraction-y bottom stuff is part of d. And that just became our favorite integral ever. The integral of e to the u is e to the u, which we can re-replace the u back in as inverse tan of x plus c. That's sort of like an old skill. Pick a u, find a du, rename everything, hope the problem which looked awful looks better. That's still happening today. Taking a step to the right column, these now all fit formats. So I'll refer back to a sign problem as format number 1. This is number 2 is tan, number 3 is secant. So when I look at this problem, I know right away this is like format number 1, because I see a root, and it's numbers minus variables. That's how number 1 is set up, because the a's are numbers, the u's are variables. So the a would be the square root of this, which is a 1. If this were a 4, a would be 2. If this were a 49, a would be 7. Okay, the a will be the root of this number. The u is the root of this thing. The u happens to be an x, because the square root of x squared is x. When you do roots of powers, cut them in half. We know that. Half powers are roots. So if this were a 20, I'd go x to the 10, for example. On top, we should check to make sure that the derivative of this is present. The derivative of our u is 1, and there's always a 1 present. So we just need to follow the pattern from rule number 1. This would be inverse sine, put the u over the a, and I don't want to write x over 1. I'm just going to write x. And if these numbers weren't here, I would put a plus c and be done. Most of your homework, you'll put plus c and be done. But if they give you numbers, we're going to have to tread back to a couple days ago. Anytime they give you numbers, you put in the upper number first. Okay, so chart, root 3 over 2 on your chart for sine. You would rather do 60 degrees, but the book only does radians, pi over 3. Root 2 over 2 for sine, you'd rather think 45 probably, but pi over 4 is what the book will insist upon. And to do the math on that, you would need a common denominator of 12, which makes this take a 4, and this take a 3. 4 minus 3 would be a 1. That grand total would be pi over 12. Let me do another sine problem. I'll just keep working to the right. I know that, I think I copied this problem down wrong. Let me see on my notes. That probably has a root there. Yeah, it did. Okay, so I intended for this to be a sine problem because, again, there's roots for sine problems, numbers minus variables. So my a is a 3, my u is an x. I should think about the derivative of the u always, but again, this time it's 1, so it's worthless like it was last time. Make sure that derivative's on top, which a 1 is always everywhere. And then this is just inverse sine u over a, x over 3. Plus c, and we're done much quicker that time because there weren't numbers to play in. This is the same format because it's numbers minus variables. My a would be the square root of 3, because we're always going to do the square root of this to decide on our a. Our u would be the square root of this. Square root of 4 is 2. Square root of this is an x. But I need to think about du while I'm on that topic. The derivative of this is a 2. I look to the top to make sure I have a 2, and I don't. So I have to insert a 2 and pay for that with a half. And a half is going to be part of the answer. With inverse sine, always put u over a, 2x over root 3 plus c. Historically, we don't like roots on the bottom, but today we've got enough work to do. We're not going to worry about that. Roots on the bottom, just live with it. This right now has a complication because this doesn't fit any kind of a format. It's going to be a sine problem in a minute. But I'm going to just let that one hang for now, because this is not a true number. True numbers minus variables, we're good. But both have variables here, so I'm going to need to adjust that in a minute, but we'll save that for a moment and go do an easier one again and come back there. So let me take a small step back to the left. This one will be a tan problem. Okay. When we look to the original patterns, tan is the only pattern that didn't have a root on the bottom. So as soon as I see this, I know I have a tan. The a would be the root of this, which is a 1. The u would be the root of this, which is an x. So I want for my answer to put 1 over a, which is 1 over 1, and I'm not feeling that. Inverse tan. Put u over a, an x over 1, that's just an x. In a different world, I'd put plus c and be done. Okay, but this one's a little bit meaner because they gave us these numbers to try out. So inverse tan of 1 is 45, or pi over 4, minus inverse tan of 0 is 0, so that's just pi over 4. If I step over here and look for tans, this is a tan problem because there's no root in it. The a would be root 10. The u would just be an x. I should think about du being 1, which is worthless. And back here, actually to the left, I should have thought about the du being 1, but that would have been worthless. So no harm done that I forgot that. So answer for tan is 1 over the a. Inverse tan, u over a, with our good friend, the plus c, a foot always. This is still a tan problem. This is my a, would get me root 7. My u would be a root of 3, and a plain old x that's not under a root. The root of x squared is just a plain old x. I should think about du is root 3. So I need to have that present, and I don't. So I pay for that with a 1 over root 3. A minute ago I did a 2 and a 1 over 2. Here I got a root and a 1 over root. So this answer would have a 1 over root 3. The rule number 2 for tan says to start off with 1 over a, so 1 over root 7. Inverse tan, always put u on top of a. And I'd be almost good with that as an answer. I should just clean this up, because I can multiply these roots together. Root 3 times root 7 is a root 21, and that's best. This will also be a tan problem, but that's also going to have some cleanup, because there is, like, you can look at this as your a, and you can look at this to be your u. You have this other piece that's causing a little bit of a ruckus, so I'm going to discard that for 1 minute and go do a different question and then clean those up. Back to this. This is a secant. I know this is a secant problem because it has variables minus numbers with other stuff before the root. So I look at this as my u to be an x. I look at this as my a to be a 1. I would make sure there was a u present here, and there is. I would do the derivative of u, which is 1, make sure that's on top, which it is. So this answer would be 1 over a, which I'm not going to write 1 over 1. Secant, bars, I can go u over a, so x over 1. And if there weren't numbers there, I'd get plus c, I'd be out of it. But there are numbers there. So we're going to need to use our chart. Secants mean it's not on the chart. You've got to flip and think cosine instead. So this is thinking upside down. This is over 1. I've got to think upside down. So cosine 1 over root 2, that's pi over 4. Cosine root 3 over 2 is 30, but pi over 6. Common denominator of 12. This would be a 3, that would be a 2, so pi over 12 is that one. Walking to the right, looking for secants. This is a secant problem because there's variables minus numbers. So the variable part gives me my u by doing a root. Square root of 4 is 2, square root of x squared is x. The a is the square root of 5. I need to think about the derivative of 2x being a 2. And then I need to look around and make sure everything is squared up. Here I need to make sure I have a u. And I don't quite. I'm lacking a 2. Up top I want a du, and I don't quite. I'm lacking a 2. But that's self-fixed. If I put a 2 on the top and a 2 on the bottom, I don't need to pay for that. I already paid for that as I was doing it. So this is just good to go. This will be 1 over a, inverse secant, 2x on top of root 5, because it's u over a, plus a c. And I'll need to erase and clear a little bit of board space, because I had one problem I couldn't quite squeeze in there in the end, which was dx root e to the 2x minus 6. This is still a secant problem, because it has variables minus numbers. Anything with variables minus numbers is a secant problem, but this is going to need some fixing. This is going to give me the u. Cut the power in half from 2x down to x. The a would be a root 6. Think about derivative of u. That's our favorite derivative. Derivative of e to the x is e to the x. To fix this problem, I'm supposed to have a u here, and I don't. And I'm supposed to have the derivative of u there, and I don't. But since it's the same thing in both places, that's self-fixing. It's okay. So this is then just a secant answer, 1 over a. And then in bars, I want to do u over a plus c. And on this one, I'm going to drop the bars. There's occasions where we know things are positive and you can drop the bars. E is a positive number, but if you take that to any power, it is positive. The bars are unnecessary. With that previous problem, we needed the bars there. Okay, so these didn't fit a format, so I saved these for last, and now here we go. So if you have something that wasn't quite right, take it on a little trip. Put the x squareds always before the x's. So I did a little bit of shuffle around in order. And we're going to have to do a thing called factoring by completing the square, which dates back to our algebra 2 days together. Factoring by completing the square, x squared can't have a thing with it, so we have to pull off any item that's in front of the x squared. So that negative is going to get pulled off to go x squared minus 4x. Let me take a step to the right, and I'll do the same thing on this other one. We'll kill 2 birds with 1 stone. This has a number with the x squared. So I'm going to pull that off of the x squared and the x. But if there's a number, I'm going to let the number just mind its own business. And you might or might not remember me making these little blanky blank spaces for a process called completing the square. This square would be x minus, because I copy the sign, 2, because I cut that number in half. That makes that a square. This blank number here, we have to take this times itself. Anything times itself is always positive. So this times itself is a 4. But in the big picture of the problem, this isn't really adding 4. This could multiply in and snag that. This is really a negative 4 in the big picture. And to pay for a negative 4, add 4. To make this look a little bit cleaner, instead of adding 4 at the end, I could put a 4 at the beginning. And that's what this problem really is this. And now it fits the pattern of a sign. The root is still present. So I just took this thing, the root is still there. This went on a little completing the square journey and came back just looking different. Okay. My a is now a 2 from doing the root. My u is an x minus 2 from doing the half of the powers down to 1. I should think about the derivative of the u, which is a 1. 1 is always present. So this answer is inverse sine the u, which was x minus 2, over 2, plus c, and that one's good now. If I go to work on this one, the square sadly has a decimal in it. It's going to be an x, always copy the sign. Half of this number, half of 1, would be 0.5. To fill in the missing link here, always a positive. This times itself is a 0.25, but not really. 0.25 really could multiply 4 anytime it wanted to. When these multiply, they'd make an add 1. And to pay for an add 1, over here I'll subtract 1. And when I total that up, it is a plus 1. So this question really isn't the way it looked. It's really a 4 x plus 0.5 squared plus a 1. And now it's definitely a tan pattern, more easily to see. This variable stuff gives me u. this number thing gives me A is 1, in the root. If I do the root of this, 4 is 2. Half of the power is just x plus 0.5. And instead of looking at a distribute problem, I think we're going to be better off to just distribute it and get 2x plus 1. I think that's going to be friendlier to us. The du is then a 2. So we need this to have a 2 on top. The derivative of u always needs to be on top. If I do a 2, I need to pay for that with a half. Then it's a tan problem, we just follow the pattern. Tan does 1 over a, so 1 over 1 is useless. Tan, u over a is 2x plus 1. I don't need to go over 1 for the a, but plus a c. There are a few in the homework that are going to have factoring by completing the square. Book homework, let me take a quick walk and peek here. We're 414, we always spend 2 days on this page. There's a 27 to 68 odd, there's a 28 to 68 even, that's day 2. They start off with sort of like the normal ones, the way I did, up to 50-ish, it looks like. 51 to 60 all have something to do with factoring by completing the squares, from 51 to 60. 61 to 8 look like they do the problem I came in on. That very first problem, before I even started the notes, I had a pick a u, pick a du, old-fashioned substitution. I did that very first note. They save those for the last homeworks. This will be there at least 2 days of homework. Sometimes it even takes a third day on homework to just continue to discuss them. Once we can get solid on the homework on 414, there's a series of practice quizzes that go from 6.5 to 6.9, and then there'd be a quiz. There's a series of tests on all of chapter 6, and then there'd be a test. But that's going to take us a good, really long while to get through all of that, but at the pace that we'll have to just sort of discuss day by day how you're doing. So, see you later, calculus.